Hello everyone, welcome back. In the last couple chapters, we have been looking at dynamics by looking at the forces acting on things and figuring out what kind of acceleration, or if the acceleration is zero, that an object would have. What we're going to do is take a little different view of things, and that brings us to our next section, section number 6, work and energy. We're going to need to introduce a new concept, a new quantity, actually a couple new quantities. The first one we're going to talk about is work. When you apply a force on something and move that object, you are doing work. This is a term, work, that we're going to have a very, very precise definition for it in this course, and we're always going to mean that definition when we use the term. You might say, oh, I have a lot of work to do if you need to study or something like that, in general, in ordinary everyday language. In physics, when we say work, we mean a very, very specific definition. Let's imagine that you apply a force on an object. So here's some object, and you apply a force on it in a particular direction. So here's the force vector. And that object moves some displacement delta R. The displacement does not have to be in the same direction as the force. So let's imagine we have some displacement in that direction, and we'll call that delta R. We will define the work done as the magnitude of the force times the magnitude of the displacement. But then it also depends on the direction, the relative directions of these. Let's imagine that there is an angle between F and delta R, an angle theta. Remember, how do we find the angle between two vectors? Let's imagine we have a vector here, the force, a displacement here, delta R. How do we find the angle between them? We put the vectors tail to tail. Always remember, to find the angle between two vectors, you put them tail to tail. These don't necessarily have to be in the same direction. We might have a force in this direction and a displacement this way. How that might happen, we'll talk about that in a little bit. But if you've got a force this way and a displacement this way, again, you put them together tail to tail. The angle between them is this angle here. The angle between two vectors can be anything from 0 degrees if the vectors are in the same direction, 90 degrees, 179 degrees, 180 degrees. The angle between two vectors could be 180 degrees if they are in opposite directions. If the force continues to go around this way, then the angle measured between them is this angle down here. It's not this angle up here. The angle is now this one. The angle between two vectors is always the smallest angle between the vectors, the closest angle between them. So vectors can be a minimum of 0 degrees and a maximum of 180 degrees. If it keeps going around this way, then the angle then is measured this way, and the angle actually starts to decrease rather than increase. So angles between vectors greater than or equal to 0 degrees, less than or equal to 180 degrees. Then, the dependence on the angle for the work is times cosine of theta. So there is our definition for work. F delta R cos theta. And let's remember what all of those terms mean. F means the force acting on an object. Any force, whatever force you want to talk about, you can talk about the work done by that force. Delta R is the displacement, the magnitude of the displacement, magnitude of the force, times cosine of theta, where let's remember, what is theta? Theta is the angle between F and delta R, the angle between the force and the displacement. That is then going to be the definition that we will use for work. I want to just point out a couple things. We can think about this in a couple different ways. First of all, let's imagine we think of that cosine theta as going along with that R, the F, so to speak. In other words, let's think of this as F cos theta times delta R. It doesn't matter what order we multiply things. We can multiply them any way we want. Let's just imagine that F that cos theta goes along with the F. What is F cos theta? Well, if we come up here to our diagram and we decompose, in other words, we make F into its components, one component along delta R, one component perpendicular to delta R, F cos theta would be this side down here, the side of F that is along delta R. So F cos theta, that's the component of F along delta R. In other words, the only part of a force that contributes to the work done is the part of the force in the same direction as the displacement. In other words, we might have a force that looked like that, which would have the same component in the direction of delta R and would contribute the same amount of work. Or this force, or this force, or this force, as long as they all had the same component along delta R, they would do the same amount of work. That's one way of thinking about this. Another way is actually to put the cosine of theta along with the delta R. We might think of this as F times delta R cos theta. Thinking about it like that, well, how would you interpret that? Well, let's take a look. Let me redraw this. I'm going to just draw delta R a little bit shorter so it'll be a little bit more obvious. Here's delta R, and here's theta. Let's decompose delta R into components, a component along F and perpendicular to F. So we'll draw a perpendicular line here. So here's the component of delta R along F. Here's the component of delta R perpendicular to F. Delta R cos theta is this side right here. And again, notice, it's the component of delta R that's along F. So another way of thinking about it is that only the component of delta R that's in the direction of the force contributes to the work. You can think of it either way, but not both. You can't say that it's the same as F cos theta times delta R cos theta. You can't put two terms of cos theta in there. There's only one. So it's either the component of F along R times delta R, or the component, or F times the component of delta R along F. So, a couple different ways to think about what this work is telling us. It's only the parts that are in the same direction that actually contribute to the work. What are the units of work? Well, we'll get the units of work right from this equation here. The units of work will be the units of force times the units of delta R times the units of cos theta. What are the units of force? What's the standard SI unit for force? It's a Newton. What's the standard SI unit for delta R, a displacement? Meters. What's the standard SI unit for cosine theta? It's not degrees. Degrees would be the unit for theta, or radians, either one. The cosine of an angle is actually a unitless quantity. It doesn't have any units. So that's what we end up with, Newton times meters. Remember, a Newton, which is a force, is a mass times acceleration. That is a kilogram meter per second squared, multiplied by another meter, gives us kilogram meters squared per second squared. So the units of work are kilogram meters squared per second squared. That combination, likewise a Newton meter, is something that we're going to see so often that it has its own name as well. 1 Newton meter, or 1 kilogram meter squared per second squared, is called 1 joule. Joule. This is not like a jewel, like a gemstone or something. This is actually named after an individual. Joule And that is the unit of work. The shortened version is just a capital letter J. So joules, the units of work. Very good. Let's stick some numbers in here. Let's imagine that a person is pulling a rolling suitcase and they are applying a force, let's say in that direction, of 75 newtons. They pull the suitcase along and the suitcase moves in this direction, let's say 25 meters, and there's an angle between the force and the displacement. If we put these together, let's imagine the angle between them is 35 degrees. So let's figure out how much work is done. The work is equal to, remember, F delta R cos theta. So F, 75 newtons, delta R, 25 meters, cos theta, cos 35 degrees. Multiply that all out, what do we get? 1,540 units of newtons times meters. What's a newton meter? A joule. So the work done is 1,540 joules. Very good. Let's take a look at some other examples. Let's imagine I take an object, maybe this calculator here, and I put it down on my table. Now I know you can't see my table, but I've got a picture of it here. So I take this, put it down on my table. So here we've got an object resting on the table. How much work does the normal force do? Well, the normal force is in this direction. How much work is it doing? Well, remember, work is F delta R cos theta. What is delta R if the object is stationary on the surface? It's zero. It's not moving. So in this case, there is no work done. The work done by the normal force is zero. Now we've got a little bit of a problem here. Work, we're going to write with a capital letter W. We have to be careful not to confuse that with what other W have we been using? Weight. That's right. So when I say this, I mean the work is zero. I don't mean the weight is zero. Unfortunately, in English, well, fortunately or unfortunately, it's the way it is, we only have 26 English letters, capitalized or lowercase, so 52 altogether. And very often they get reused for different things. So we've got to be careful and make sure that we keep track of what we're talking about. Hopefully, from context, we'll remember what we mean. In this case, we mean the work is equal to zero. How much work does the weight do in this case? Again, if it's stationary, there's no work done by the weight. The work done by the weight work is zero. All right, let's try something a little bit different. Let's imagine I hold my calculator, but let's move it. Now I'm going to walk this way at a constant velocity. How much work am I doing during this motion as I walk at a constant speed? How much work am I doing? Well, let's think about that. Let me redraw this. All right, there's my hand holding this object, and I'm moving that way. How much work am I doing? Well, what's the direction of the force that I am applying? If I walk at a constant speed, it is not accelerating in that direction. So there is no net force in that direction. The force that I am applying is straight up. So the only force I am applying on this object is straight up. My force is this way. What's the direction of the displacement? The displacement is that way. So how much work am I doing? Again, zero. Why zero work? We've got a force, we've got a displacement. Why is the work zero? Think about the angle between the force and the displacement. In this case, the force and the displacement are perpendicular to each other. In other words, the angle between them is 90 degrees. What's the cosine of 90 degrees? It is zero. So there is no work done on the object. Even though we have a force and we have a displacement, there is zero work done. Let's try something a little bit different. Let's imagine we're pushing on this object, but now we are actually pushing on it to the right, and the object moves to the right. So here's our force, and here is our displacement. And so, is work done? Do I do work on the object? In this case, yes, I do work on the object. What is the angle between F and delta R in this case? 0 degrees. And cosine of 0 is 1. So the amount of work done in this case would be non-zero. There would be some work done. What about any other work? Are there any other forces acting on the object? Well, there's a normal force. How much work does the normal force do? Again, 0, because the normal force, again, is perpendicular to the displacement. So the normal force does 0 work. What about the weight? The weight is also perpendicular to the displacement. The weight, mg, that's down, also perpendicular to the displacement, so 0 work is done. Anything else? What if there's some friction between the ground and the box, or whatever this is? What direction is the frictional force? The frictional force would actually be in the backward direction. Let's say some kinetic friction. Does the friction do work? It does. How much work? Well, what's the angle between the frictional force and the displacement? It's 180 degrees. So in this case, the displacement and the frictional force are in opposite directions, and the angle between them is 180 degrees. What's the cosine of 180? It's -1. So in this case, the frictional force would actually do negative work. It's possible for a force to actually do negative work. So here's an example where I might be pushing it forward, the block is sliding, however, the frictional force is in the opposite direction to the displacement. So in this case, it's actually possible to do negative work whenever the force is more than 90 degrees from the displacement. You're going to end up with a negative amount of work done. Okay, very, very good. How is all of this going to help us solve problems? What are we going to do? Well, let's take a look rather than just the work done by a single force, and we can figure that out. We can always figure out how much work does a particular force do. But what about the total work done on an object, the net work? In other words, the work done by the net force on an object. So the total work is the sum of all work done on an object. Work is work done by a force, and then total work is then also the work done on the object by the total force. You can add all the works together, or you can add all the forces together and then determine the work done by that total force. So let's do that. Let's take a look at that and see what we get. Let's imagine we've got some object with some net force acting on it. So whatever forces are acting on it, we add them all together. The total force acting on the object is then some force in this direction. That's the net force. The object is then moving, and it moves from here over to here with some displacement delta R. And let's imagine there's some angle theta between the force and the net force and the displacement. The total work done, the net work done on the object, is then going to be F net delta R cos theta. We are free to choose our coordinate system any way we want. For simplicity, I'm going to define my x-axis along the displacement. So I'm going to define the displacement delta R as lying along our x-axis. So whatever distance this thing travels, I'm going to write that as delta x. That's the displacement in the x direction. And we can define our coordinate system any way we want. Now let's group this cosine theta with F net. Remember, F cos theta, we saw that was the component of F along the displacement. But if the displacement is in the x direction, what's the component of F in the x direction? That's the x component of F. So we can write this then as F sub x, and let's remember this is the x component of the net force. times delta x. This is the x component of the net force. What does Newton's second law tell us? Remember, F equals ma, where F is the net force. If this is the net force in the x direction, this must equal max. In other words, the mass times the acceleration in the x direction. So we'll write this as max, that's F sub x, times delta x. Excellent. Now, you might think of delta x as x minus x naught, something like that. The displacement in x, let me just write that as max times x minus x naught. I do that just because it might make this, you might think of this a little bit more readily, so to speak. Look at that term right there. Ax times x minus x naught. We've seen that before. We've seen that combination of terms. Where have we seen that? We've seen it in one of the kinematic equations. And if you'll remember, the fourth kinematic equation. Let's write that down and let's see how we might manipulate this equation using that kinematic equation.